All right, let's jump right into this. Welcome to today's Explainer, where we're going on a seriously fascinating journey. We're taking abstract human problem-solving concepts and tracing them all the way down to how a computer actually executes our commands. Today, it's all about mastering that bridge between concept and code. We're going to take a deep dive into object-oriented programming and, of course, the Java language itself.
Here's a quick look at our roadmap for today. We'll be hitting 5 key areas: programming paradigms compared, the core principles of OOP, the features of Java, the compilation process, and finally, we'll wrap up by decoding some essential Java terminology.
Okay, starting off with Section 1, Programming Paradigms Compared.
Programming is quite simply the act of giving a computer a specific set of instructions to perform a task. Historically, the standard approach was procedural-oriented programming, or POP. This methodology treats software as a top-down, sequential list of instructions. In a procedural model, functions operate on global variables that move openly between different sections of the code. As applications scale to thousands of lines, any of these scattered functions can access and modify that shared information. This open movement makes core data highly vulnerable to accidental corruption during execution. Because procedural systems cannot guarantee data security as they grow in complexity, developers required a new way to architect software. Object-oriented programming addresses these vulnerabilities by modeling software around real-world entities. This shifts the focus from a sequence of functions to the objects themselves. This comparison table highlights how the two methodologies differ in their treatment of data and security. Look at row 3, which states that each object controls its own data. Row 6 confirms that these objects interact exclusively through method calls and message paths.
Moving right along to Section 2, the core principles of OOP.
These 4 principles basically mimic physical reality. The first one is abstraction. Simply put, this means showing only the essential features while hiding all the background details and internal workings. No need to memorize this blindly. Let's make it real.
When you go to an ATM, you just insert your card, punch in your PIN, and grab your cash, right? You don't need to know how the bank's internal servers are communicating at that exact second. That is abstraction. Or think about a car dashboard. You just use the steering wheel and the brakes. You definitely don't need to stress about how the pistons are firing inside the engine.
Our second principle is encapsulation, which is bundling data and methods into a single unit. Picture this like an impenetrable protective wrapper around your most valuable information, keeping it totally safe from outside interference. This is also known as data hiding. A perfect real-world example is literally a medicine capsule. The outer shell safely packs all the powder and medicine inside. In computer programming, a class acts as that protective outer shell, and your data is the medicine inside.
Pillar number 3 is inheritance. This is a mechanism where a new class, which we call a subclass, takes on the properties and behaviors of an older class, known as the superclass. Those are crucial keywords, by the way: subclass and superclass. And the biggest benefit here? Massive code reusability.
Just like a child inherits physical traits from their parents, code works the same way. For instance, you could have a general vehicle superclass that has common things like wheels and an engine. Then car and motorcycle would be subclasses. They automatically inherit all those great features from the vehicle class, while also adding their own unique specific features.
The fourth and final principle is polymorphism. Look at the Greek roots here. Poly means many, and morphism means forms. So, many forms. It's the ability of a single method to behave entirely differently depending on the context.
This maps perfectly to our daily lives. Think about yourself. You are one person, right? But you act like a student in a classroom, a customer at the grocery store, and a child when you're at home with your parents. One entity, many operational forms based on the context. That's polymorphism in a nutshell.
All right, Section 3, features of Java.
Now that we've nailed down the OOP concepts, let's look at the language that actually brings them to life. Java's immense power and global popularity come from a perfect combination of 5 key features. It's simple to code. Robust, meaning it's incredibly strong and error-free. Secured, object-oriented as we just saw, and crucially, platform-independent. That means you can write your code on one computer and run it on a completely different operating system without changing a single thing.
Section 4, the compilation process.
It was designed to run on any hardware without modification. This write once, run anywhere capability is made possible by a two-step execution architecture. It begins when human-readable source code is sent to the Java compiler. Instead of creating code for a specific processor, the compiler translates that source into a secure intermediate format. We call this format bytecode. Because it isn't tied to any specific operating system, it is the key to Java's portability. To run the program, a Java virtual machine, or JVM, reads the bytecode line by line and translates it into the final machine-specific executable code for that particular computer. This two-step process completely ensures that the object-oriented logic developers write remains securely and universally deployable on any given hardware.
Let's break down these foundational terms for your notes. Source code is simply the original code written by you, the programmer, and the compiler? That's a translator program that takes your entire source code and converts it into bytecode in one single go, getting it ready for the machine's next step. Next up is bytecode. This is the intermediate step that actually makes Java platform independent. The computer's processor can't read it directly just yet. That's where the interpreter comes in. While the compiler translates everything all at once, the interpreter reads this bytecode line by line, executing it step by step. So the crucial point here is clearing up the classic acronym confusion between JVM and JDK. The JVM, or Java Virtual Machine, is the actual engine that provides the environment for your program to run. Without it, bytecode does nothing. On the flip side, the JDK, or Java Development Kit, is the complete toolset you use right at the beginning to write your code and actually develop the application. After all those steps, we finally arrive at executable code. This is your code's final destination. It's the actual machine-readable language, those raw zeros and ones, that the computer's hardware processor can directly understand and perform tasks with.
And that wraps up our explainer for today.